Modern computers came from a long way of history. Primitive computers is enormous enough it can fit a whole room and its capability is limited. I'm Canja from BSEE 3A1 and this is the summary of CPU architecture. The CPU you see now is not the same CPU as it was years ago. But what do CPU do? The CPU do what we want them to do. And the CPU is being contained in a silicon, which follows the Moore's law, which states that we can double the number of transistors per unit area about every 2 years. So the first computer is the ENIAC, or the Electronic Numerical Integrator and Computer. ENIAC is the first general-purpose digital computer, unveiled in 1946. You all curious where the term bug comes from? The bug term used today is a jargon used by Grace Hopper in 1946 as he discovered a bug, which is a moth, in working with Mark II and Mark III computers. The size of the moth bug found in that day cannot be compared on how small the silicon die is nowadays. We have here John von Neumann and Robert Noyce. These two persons paved the way of modern processors. John von Neumann popularized a new architecture, or the idea of stored program computer, while Robert Noyce patented the first monolithic integrated circuit, which combined multiple transistors in a silicon chip. So we have here our timeline. In 1950, semiconductor-based transistors was introduced in the market. In 1968, Robert Noyce paired up with Gordon Moore to found Intel, or the Integrated Electronics, where they unveiled the Intel 4004 in 1971 with a whopping 2,300 transistors and 740 kHz. It is the first general-purpose programmable processor which packed all the computational power of the ENIAC. In 1972, Intel unveiled the 8-bit microprocessor, the Intel 8008, where later on, in 1974, they unveiled the 8080, which has a x86 ISA, which is one of the world widespread processor. In 1979, they released the Intel 8086, that is a 16-bit with x86 ISA, which became the foundation of modern CPU designs. So next, we have here the instruction set architecture. It is a set of instructions that defines what kind of operations can be performed in hardware. It is the language of computers. It is sometimes called as architecture or computer architecture, which is the abstract model of computers. It also bridges the hardware to the software. ISA describes the memory model, supported data types, registers, and behavior of machine codes. So what is happening in the hardware and software aspect of the CPU? In a hardware level, the ISA is used as instruction design spec that tells the engineers what operations to execute. While in a software level, the compiler uses the ISA to transform code from C, Java, or Perl into machine codes instructions or language that the CPU can process. We have here the microarchitecture. It is an implementation or specific design of an instruction set architecture. The CPU's pipeline. What is a CPU's pipeline? Pipeline is very similar to an assembly line. The more stages are added, the less is done in each individual stage. The more pipeline, the faster each stage can run, and the more stages are being done in parallel. The CPU's pipeline consists of 4 stages. The fetch stage, where it retrieves the instructions from memory so that the CPU knows what programs once executed. The decode stage, where it decodes the fetch instructions into native operations. The execute stage, where the operation CPUs perform depending on the ISA. And the write back stage, where the CPU will store those results. These are saved locally in a register, and sometimes they are stored in a memory or a cache. So the fetch stage and the decode stage collectively is called the front end. And the execute and the write back stage is the back end of the microprocessor. Next, we have here the branch prediction, where its purpose is to attempt to guess whether a conditional jump will be taken or not, or true or not true. Branch predictors today can oftentimes record and understand and learn the past history. Next is the speculative execution. It is when a microprocessor executes newer instructions than a branch without knowing if the branch is stake or not, if the branch is true or not true. This is a fundamental component in modern microprocessors for achieving great performance. The cache. The cache helps offset the long round-trip time to main memory and back. It keeps local copies of main memory internally in structures. The cache has a special version, which is the instruction cache, where it can read instructions in just 1 to 2 cycles instead of the hundreds it may take to go to the main memory. A microprocessor has a microoperations. Microoperations is the second half of the front end, where the program's instructions are decoded into microarchitecture's internal operation. This is the strongest connection between the ISA and the microarchitecture. Almost all modern microprocessors are superscalar. Superscalar execution is the implementation of many ALU, and when those ALU can operate in parallel. It describes a microprocessor design that make it possible for more than one instructions at a time to be executed during a single clock cycle. So in-order execution is a basic microarchitecture. The microoperations are executed in program order, but in order to provide the best performance and energy efficiency, executing them out of order is more favorable. The first step in an out-of-order back-end is to take the microoperations provided by the front-end and determine their dependencies. These dependencies is being tracked by register renaming. Dependency is where the microoperation is said to be dependent on older microoperations when it needed its result to do its own. The whole CPU process is much more complicated. This process is being refined up to date and innovations is still being done to give a more efficient, accurate, small yet powerful microprocessors. The next decade, we can expect a superior type of microprocessors in the market available for everyone. I'm Kent Justin Canja of BSEE 3A1, and that is the summary of CPU architecture.